Students, title of today's lecture is Contact Resistance Measurement Technique. So in the previous lecture, you have seen what is contact resistance and how it can affect the device performance. So today we will see how to measure this contact resistance in case of semiconductor devices. In the last lecture itself, you have seen that there are various techniques for finding out the contact resistance. So these techniques are summarized here. So the first one is the two contact and two terminal method. Then second method is multiple contacts, two and two terminal. Then there is a four terminal method and six terminal method. But remember, all these methods, they measure rho C. They do not measure rho I. Rho C means specific contact resistance. Rho I means interfacial contact resistance. So the interfacial contact resistance is theoretical concept. So it cannot be measured experimentally. Experimentally, we can find out only rho C. So this concept, this fact we discussed in the last lecture also. And you know that if we talk about rho C, it includes the metal semiconductor interface plus some part in the metal just above the contact, some part in the semiconductor just below the contact, and some current crowding effects are also there. So all those effects they contribute to the rho C, and experimentally whatever we calculate, that is rho C. Rho I is a theoretical concept and it is purely like interfacial contact resistance or interfacial contact resistivity, which is difficult to measure experimentally. Now we will discuss these techniques one by one. So the first technique which we are going to discuss is two contact two terminal method. So this is one such situation. So this contact which is formed here in this figure, that is a vertical type contact, because the current which flows here within this structure, that is vertical current. One contact is on the top of the semiconductor. This is defined photolithographically because this contact is in a small window opened in a oxide layer. This part is oxide layer, this side is also oxide layer, and this contact is opened within this window. The second contact is the bottom contact, and the whole bottom surface of this wafer is contributing towards this back contact. So as a result of one contact on the back side and one contact on the front side, current within this semiconductor will flow in the vertical direction. So if this kind of situation is there, this is known as a vertical two terminal contact resistance structure, right? Two terminal means one terminal for measurement is here and the second terminal is here, right? So if this kind of structure is there, then the total resistance between these top contact and bottom contact, that equation, that resistance is given by this equation. For this measurement, we allow a known current to pass through this structure and we measure voltage across this structure. So now we know the current because this is supplied by us. V is measured with the help of voltmeter. So by taking the ratio of I and V, or you can say using Ohm's law, we can find out the total resistance. That measurement is experimental measurement, and that total resistance will be equal to this part, this factor. So this Rc is the contact resistance of this contact. Rsp is the spreading resistance which is coming into picture because of this top contact. Rs is the resistance offered by this semiconductor part from top contact to bottom contact, and Rcb is the back contact resistance. You see, this Rc and this Rcb, these two are contact resistances. This is the front contact resistance and this is the back contact resistance. And 2Rp is, you can say, the probe resistance, front side probe and bottom side probe. Remember here that this RCB, back contact resistance, will be small as compared to RC because the back contact area is very large. So this resistance will be very small. So often it is negligible resistance. So only one RC that is coming from this front contact, that will play some role. So from this equation, if you know spreading resistance, if you know RS, RS is the semiconductor resistance, This 2 rp is most of the time negligible, so you can ignore this part. Then it is possible to find out this contact resistance. This RCB, that is also very small. So anyway, so we will have more detailed discussion about this vertical structure in the coming slide. So this part was the case when the vertical current is flowing, or you can say the vertical contact. Second possibility is this kind of horizontal contact, or you can say the lateral contact. This is a lateral two terminal contact resistance structure, right? Lateral means the current is flowing in the semiconductor near the surface, just like this. So as per the external arrangement, the current will move from this contact to this contact, because the current is coming down like this. Like so it is a horizontal current, or you can say the lateral contacts are there, and these two contacts, they are on the same side of wafer, so that's why we call them horizontal contact or lateral contact. So this figure is the side view of this structure, and if we are interested to look at the top view of this structure, top view will look like this. You can see here, this is oxide or some dielectric material. Within this dielectric material, two circular windows are opened using photolithography, and the metal contact is within this part. You can see here, one metal contact is here and second metal contact is here. So this metal semiconductor contact, that is taking place within these two windows, and we are assuming that these metal semiconductor contacts are ohmic contacts. Okay. So this is the structure of a lateral contact, and if we talk about this lateral contact total resistance, so experimentally what we do, we are allowing a non-current I to pass through this structure, and we are measuring voltage potential difference between these two contacts with the help of voltmeter. So using this IV ratio, we can find out a resistance, and that total resistance is RT, and this RT is coming because of these factors. Now you see here, there is two RC. Two contact resistances are there, one contact resistance because of first contact, second contact resistance because of second contact, and two spreading resistance components are there. Both contacts will contribute some spreading resistance also, so those resistances are also to be included here. RS is the resistance offered by the semiconductor part between these two contacts. So this whole semiconductor, that is offering some resistance, so that resistance is taken care by this RS parameter, and 2 rp means the probe resistance. Now you can see here, if you compare these two, so only one RC was there. Here there are two time RC, because both the contact areas are equal contact areas, and so they are supposed to contribute equal contact resistance. While in case the second contact was back contact, its area was much bigger than this top contact, so that RCB is normally very small as compared to this. Now in this lateral contact structure itself, so if we talk about the spreading resistance, so the approximate value of spreading resistance is given by this. The C is the correction factor, rho is the resistivity of semiconductor. So because in order to find out this RC, our purpose is to find out contact resistance. So we should know all other values. RS is the resistance of the semiconductor, that we can find out using formula method, something like this. This 2 rp we can ignore because that is very small. But if we want to find out RC, we cannot ignore spreading resistance. So total resistance that we are measuring experimentally with the help of this experimental setup. And this is the spreading resistance. The C is correction factor. Rho, I told you, is the resistivity of the semiconductor. R is the contact diameter. But this equation of spreading resistance is valid in this particular case when this 2T is the thickness of this wafer. So the 2T is very large as compared to R, or you can say this contact radius is very small as compared to the thickness of this wafer. In that case, spreading resistance equation will be given by this. So let's have some more discussion in the coming slides about these structures. So if we talk about this vertical structure, so you have seen in the previous slide that the total resistance is given by this equation. RT we are calculating experimentally. So if you ignore this RS, because this is very small, approximately it's not zero, but it is very small as compared to other parameters, so we can ignore it. This back contact resistance, I told you, it's also very small because the contact area is much bigger as compared to the front contact, so that is also negligible. And this probe resistance is negligible, of course. So if we ignore all these, right, or means if we consider that all these three values are very small, in that case, its contact resistance will be RT minus spreading resistance. It will be given by this equation. RT experimentally we are calculating from the known value of I and the measured value of V. The Ohm's law we can apply and we can find out RT. This R spreading resistance, it's very important parameter. So in order to find out RC using this technique, it's important to find out the spreading resistance. And you know that measuring spreading resistance is a very you can say tricky part. It involves a fabrication of a particular type of structure, a lot of readings you have to take, only then it is possible to find out spreading resistance. So in short, you can say that if you are using this kind of structure for measuring the contact resistance, then it is very difficult to get this value, because even if you make other values small, spreading resistance you cannot ignore and you have to put this value here. So knowing spreading resistance with the accuracy is the main requirement of using this particular structure for finding out contact resistance. The another way is that that spreading resistance becomes very small as compared to R, right? And that can be made possible if we use small radius contact, because spreading resistance, you know, depends on the contact resistance. So it depends on the radius of the contact. So small is the radius, spreading resistance can be reduced like that, but it becomes very tricky, because even with that, spreading resistance is there and you have to put the value of spreading resistance here. So how accurate it is, that determines the accuracy of this measurement technique. So the vertical structure you have seen, what kind of difficulty is there? The involvement of spreading resistance, its accurate measurement is the prime condition for using this structure. Now let's go to the lateral contact, horizontal contact. Sorry. You see, this is horizontal contact. So this structure you can see here, the structure is given here. So this is a p-type semiconductor, and within this p-type semiconductor, n channel is created. And if you look at the top view is here. This is top view, this is side view. Top view, you see, this is whole p-type structure, whole p-type substrate, and within this p-type substrate we have a n channel. This is rectangular n channel, and at the two ends of this channel, so this end and this end, we have two contacts. So if we look at from the top, this black part, this is one contact, and the second contact is this. So if you look at the side view, this is one contact is here, and the second contact is here, right? So we are supplying a current from this side, so that current is traveling through this channel and it is collected by this second contact, like this current is coming out here. So I we are supplying, we are measuring with the help of high impedance voltmeter. So that way we can find out what is the total resistance between these two contacts. And remember, this is horizontal structure because both contacts are on the same side of wafer. So the total resistance which we can find out experimentally, that will be equal to these parts. So this part is the resistance offered by semiconductor between this contact and this contact. The second part, so I will tell you like this. This RD is the resistance due to current crowding under the contact. So that current crowding, that contribution to the resistance, you have to measure first before using this equation for finding out the contact resistance. And RW is the contact width correction. So that correction you have to apply if Z is the, you can say, width of this contact. You can see here in this figure, and W is width of the channel. So normally what we expect that this Z is equal to W. The contact width is equal to the width of channel. So that is the ideal situation. If that happens, RW is 0. There is no correction required. But practically, we keep this Z sorry, little smaller than W, because we want to avoid the possibility of any overlap. because if this Z is equal to W, then there are chances that during fabrication, if there is slight misalignment, this contact will go to this P type portion also. So the P type and N type, they will get shorted, and whatever measurement we will doing, all these measurements will disturb. So because in order to avoid that misalignment, the Z is little smaller than W. Intentionally, you can say it is smaller than W. So it means definitely there is some correction factor involved here. So anyway, so even if this RD, RW and these parameters, they are ignored, still there are some issues here. So this part is the resistance offered by the semiconductor. So it means you should know the sheet resistance of semiconductor, or you can say the resistivity of semiconductor in advance if you want to calculate RC from this equation, right? So if you have any confusion that how this part is there, so this part is actually you can say this is the resistance offered by the semiconductor, right? So you know that so equation of resistance is resistivity into uh, D by A, right? D is the length or the gap between these two contacts. D is the, you can say, length of this channel, and A is the cross sectional area. And A, you know that A is given by cross sectional area here, that will be given by W. W is the width of channel multiplied by T. T is the thickness of this channel, you can say. The T is from here to here, right? So W into T, so I am putting this T here, right? And this rho by T, you know, that is sheet resistance. So what we have done here, this R, which is resistance of semiconductor, that is sheet resistance of semiconductor multiplied by D divided by W. So if you have any confusion how we got this parameter here, so why I am not writing RS, instead of RS I am writing all these in terms of sheet resistance. So it came because of this, right? So anyway, the main conclusion from this slide is that if you want to use this kind of lateral contact two terminal structure for finding out contact resistance, so you should know the contribution of this current crowding RD, and if there is any correction factor, they are definitely there. But even if you ignore them, it is important for you to know the value of sheet resistance. D and W is not a problem because they are design parameters from your structure, you know them very well. D is the gap between these two contacts, or you can say length of the channel, and W is the width of the channel. So these values you know, but since you don't know sheet resistance, you cannot find out RC from. So the accurate measurement of sheet resistance is the prime requirement for measuring contact resistance using this technique, right? You know, in case of vertical contact structure, the spreading resistance was measurement of spreading resistance was important to know the contact resistance, and in this lateral contact structure, measurement of sheet resistance of this diffused channel is the main requirement for getting accurate value of contact resistance. Now you have seen a two terminal structure, and you have seen their limitations also. So now we are going to second type of technique for measuring the contact resistance, and that is multiple contact two terminal method. So now we will discuss the structure, or we will use the structures where we have more than two contacts, multiple contacts, but two terminal. Two terminal means during one measurement we will use only two terminals. Sorry. So you can see this structure here. Again, this is a p-type semiconductor, and within this p-type semiconductor there is a diffused n channel, and there are three contacts. These contacts are made to this diffused n channel: contact 1, contact 2, and contact 3. So that's why we are calling it a multiple contact structure, but it's a two terminal because at a time we are using either 1 and 2 or 2 and 3. So that kind of measurement we are doing. So at a time we are using only two terminals, 4 measurements. So that's why it is known as two terminal method. Otherwise, the physical contacts, if you talk about, the number of physical contacts is more than 2. So this is the side view and this is top view, you can see here. So again, you can see this, the only channel is shown here, and within this channel there are 3 contacts. 2 contacts are at the end of right end and left end of the channel, and there is third contact that is between in between the channel. But remember that distance between first and second contact and distance between second and third contact, that distance is not same, right? Intentionally that distance is kept different. So suppose D1 is the distance between first contact and second contact, and D2 is distance between second contact and third contact, and D1 is not equal to D2, remember. So now using the same method, that is uh, at a time we will use only 2 contacts, so we are calling it 2 terminal. So the current will pass through, suppose, first channel, and it is coming out of the second contact. So the voltage difference is measured between first and second with the help of voltmeter. So that way we find out RT1. RT1 means the total resistance between first and second contact. In the same way, we will repeat this measurement between second contact and third contact. So in that case, we will get RT2. Second, you can say the total resistance. So two resistances are there. So in general, the equation of these two resistances, that is given by this, right? So RTI. So if it is between first and second contact, then it is RT1. If it is between second contact and third contact, then it is RT2. So that is equal to this. So this is sheet resistance D1 divided by W, right? All these parameters, this is the resistance offered by the semiconductor between the contacts, plus 2 RC, 2 contacts. So if this, in case of RT1, first contact and second contact, both contacts are offering some contact resistance. So that will appear as 2 RC here in this equation. So similarly, if we talk about RT2, then it will be RT2. So RSH will remain same because the same semiconductor is there. W, width of the channel is same. D, D is different between, because in case of RT2 we are working with second and third contact, and now D is different here. So D2, and the contact resistance in this second measurement means in RT2 also, that is going to remain same because while fabricating this whole structure we have maintained this thing that the contact area and all the processings involved in the fabrication of contacts, all those processings are same processing. So we suppose that the contact resistance offered by all these 3 contacts is same resistance. So that way we will have two values of total resistance, or 2 equations of total resistance, and the variable here is D, only D, and this RT. 2 variables are there. So you can consider that whatever equation of resistance we are getting here, that is a linear equation in 2 variables, and if there are 2 equations, easily we can find out the value of those variables. So that mathematics you have learnt in your high school. So from that, if you find out RC with the help of 2 equations of total resistance, the RC will be given like this. So I can just give you an idea that from first equation you find out RSH by W, and then substitute that value of RSH by W in the second equation, and then you will be able to find out RC, because RC is same in both equations. So anyway, so whatever method you use to solve those linear equations to find out this RC variable, you will get equation something like this. So you see here, this is very interesting equation, because in this equation uh, there is no RSH, sheet resistance of semiconductor, doesn't appear here. Rho S doesn't appear here. Spreading resistance doesn't appear here. So that way it is very easy as compared to earlier 2 methods to find out contact resistance using this method. RT2, RT1, they are experimentally determined values, D1 and D2. So these D1 and D2, these are the gaps between the contacts that you can measure in the structure. So let's have a little more discussion about this multiple contact to terminal method. So this equation you have seen from the previous slide. So this equation doesn't have, uh, so you can say this RC is independent of rho S, means resistivity of semiconductor. Rho S or RSS, sheet resistance of semiconductor, they are not appearing in this equation. So even if you don't know the sheet resistance, doesn't matter, you can find out contact resistance. So whatever is the accuracy of measurement of sheet resistance, that also doesn't matter because sheet resistance is not appearing in this equation. Now the accuracy here, that depends on the measurement of D1 and D2. So if there is an inaccuracy in the measurement of D1 and D2, that inaccuracy will make this whole process inaccurate, right? So you can say that D1 and D2 are the source of inaccuracy. If there is any inaccuracy, that will come because of the measurement of D1 and D2, right? So you have to be careful in measuring the D1 and D2 if you want accurate results using this technique. Now, what you have got in this equation, that is RC. It is not rho C. Remember, rho C is specific contact resistivity and RC is contact resistance. So we are measuring here contact resistance. We are not measuring contact resistivity. Why? You can say that what's the special thing here? Because if you want to find out rho C is simple. Just you put RC here and divide it by the contact area. Contact area may be pi r square, right? Here this r is radius of the contact. So anybody can say that if you know RC, there is no big issue or any like hurdle in getting rho C. But I am saying we cannot measure rho C using this test. So what is the reason for this? Reason is that so here we are assuming that so it is R by A actually. So it's area. So the area, this area is the physical area of this cone. We can find out this area very easily. So here I'm writing pi r square, but since it is a rectangular contact, so the area is z multiplied by this length of contact, right? So you can say that this is r into, if we talk about area, then it is z into L. L suppose is this length of contact. So this length of contact, right? So area is this. So you may ask that simply using this equation, it is possible to find out rho C. But now I'm saying we can determine RC but not rho C. Why? Because for that we should know this area accurately. Or you can say we should know this Z and L actual. But that is not possible because the contact area which we are mentioning here, that is not the exactly known contact area, right? So what we know from this structure, that is the physical contact area, but it is not the effective contact area. All this contact is not being used in the current collection or current delivery. And if all this portion is not used, we cannot use this formula for this, right? So that's why it is difficult. So in the coming slide, this concept will be more clear. So in order to get the more understanding about this particular issue, where we say that the contact area is not exactly known, or you can say the physical contact area is not the actual contact area. So there is one model developed by the researchers, and okay, so the only part of this contact length about the diffused layer thickness is active for the current path, right? So whatever I was telling you just right now, the same point is here. So in order to understand this concept in more detail, so there is a transmission line model developed by researchers. You can see here. So this is structure, this is p-type substrate, and on the p-type substrate there is n-type channel. So suppose current is coming from this side, right? So I'm not showing the second contact here, only one contact is shown here because that concept which I'm going to explain, for that only one contact is sufficient. So second contact may be somewhere here, and from that second contact the current is inserted here and the current is traveling through this channel, like, right? And when it reaches to the second contact, the current distribution is like, you can see here, all the carriers which are forming this current, they have been collected by this contact within this itself. Now suppose L is the length of this contact, right? You can say the physical length, but the current is collected only by this portion, right? The whole collection of the charges, electrons which are traveling as a part of this current, they have been collected by this part also. So this is known as LT. We can say the transfer length. Only that length of contact which is involved in transferring the carriers from semiconductor to the metal. And this part is not actually being used. So when we are talking about the area of the contact, we are defining this area on the basis of its physical dimension. So we are saying that the area of contact is L into Z. Z was width of the contact and L is length. But since this part is not involved here, so we cannot say that this is a true equation. So true equation will be this LT, which is that length which is actually being used, multiplied by Z. So that is the true value. But we don't know this true value of area, and because of this, it was difficult to find out the contact resistivity in case of earlier slide, right? So because from physical structure we know only this area, but that whole area is not in the use. Now, in order to understand this concept in little more detail, so what we have done here, so this part here, that is represented with the help of this kind of resistive network. So the semiconductor metal contact, that is represented by rho c. Rho c is the, you can say, the contact resistance, contact resistivity. This is rho c here. So that is between this metal contact and semiconductor. So that is a vertical component. And RSS, this combination. RSS means sheet resistance. This is sheet resistance of semiconductor. So this is the resistance offered to this horizontal current. So this resistance is shown here like this. All these components, they are sheet resistance of the semiconductor. They are same. RSH, 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 RSH. Rho C, Rho C, Rho C. This is the contact resistance. So all this portion where the current is being collected, so that is represented with the help of this kind of network of Rho C and RSH. And with the current choosing the path of least resistance. So when the current passes through this portion under the contact, this current of course chooses the uh, less resistive path, right? So that is natural behavior of the current. Now, when this current follow this less resistive part, and also because of this kind of network of the resistances, so the voltage drop will occur if we move from this end of the contact to this end. So suppose this is L is the length and this direction is X direction. So at this 0 means at the beginning of this contact, if we assume some voltage here, right? So when we move towards this side, this voltage will keep on reducing because of this resistive network. So it is very interesting to see the behavior of or the variation of this voltage as a function of x, means as we travel from this end towards this end. So the equation is given here. So no need to go for the derivation of this equation. So just you have to remember this equation. So of course the current depends on I, the current depends on L, how much is the length, the maximum length, or you can say physical length of the contact. X is the distance from this S. As we are starting from here, this X is 0. As we are moving, this X is increasing, and when we reach to the second end of the contact, this X is equal to L. LT is that length of the contact which is actually used in the transfer of the carrier. Z, of course, is the weight. So the variation of voltage as a function of x will be given by this equation. So LT, you see here, LT is given by this formula. It's very important to look at this. So this LT, transfer length, means how much portion of contact is actually useful in transferring the current. that depends on the contact resistance or contact resistivity, that also depends on the sheet resistance of the semiconductor. So if the contact resistance is large, you see, suppose the contact resistance is large, you can see from this equation it is directly proportional to this. So we expect that this transfer length will increase, and that you can see here. Suppose this rho c is large. Now the current which is reaching to this part of towards this contact side, so that current will face difficulty in order to get transferred to the contact, because this rho c is large. So it will try to move little further in the semiconductor itself, right? So that it can easily get transferred to the contact from little far from this end, right? So that way this LT will increase. If contact resistance is large, so this current will try to move little more within the semiconductor itself before being collected by the uh, contact. And if this contact resistance is small, so when it reaches here, it will try to go towards the contact side because this contact resistance is small. So in that case, this LT will be small. So now if we look at the effect of this semiconductor sheet resistance, you see, if semiconductor sheet resistance is large, so it is inversely proportional to LT. If the sheet resistance is large, LT will be small, because you know, if the sheet resistance is large, current will try to follow low resistance path. It will try not to travel more into the semiconductor. So it will try that before getting before moving. I mean, instead of moving within the semiconductor, it's better to get transferred to the contact itself. So if more is the resistance of the semiconductor, LT will be small, because more and more current will be collected by this contact within a short transfer length, right? Now this Vx, as I told you earlier also, that it is the potential distribution under the contact. So how the voltage changes as a function of distance under the contact. Z, I already told you, its contact width, and LT is actually 1 by E distance. So what it says that suppose in the beginning near this end, if V is 1 volt, right? So LT is the distance after which, so if we talk about that 1 volt here, then after covering this LT, voltage reduces, of course, because there is a resistive network here, and it becomes 1 by E times this V, right? So the reduction is this much. So you can define this transfer length as the length after which voltage reduces to 1 by E times its original value, right? So I hope that now you have some understanding about this transfer length, because this transfer length is the effective length which contributes to the delivery of current and collection of current, and it is always less than the actual physical length of the contact. So you can see here the same structure, and here in this graph you see the voltage distribution as a function of x is plotted for different values of contact resistivity. So this is normalized potential under the contact versus x. So x-axis is x, this distance from this end, right, from here to here. Now x0 is the contact edge. This edge of the contact, that is something where x is 0, and as we move towards this side, this x is increasing. So the L means this contact length. This contact length is 10 micrometer, right? But this is physical length of the contact. This is not effective length. This is not LT. LT will be smaller than this. And this sheet resistance of semiconductor is also constant. It is given here, and you can see here, if the contact resistance is 10 to power minus 8, if this contact resistance is very small, right? So out of all the four different values, this is the smallest contact resistivity case. You see here, this voltage reduces to almost 0 within 2 micrometer. So instead of traveling through whole this contact, the current will travel only within 2 micrometer, and within 2 micrometer all current is collected here. So voltage which initially it was 1 here, it becomes 0 at this point. This is 1 volt here, right? and here it is 0 volt. The whole voltage drop will occur within this part only, because only this part is used in the current collection. So this is not being used here. So LT is from here to here. But remember, when this contact resistivity that is increasing, it becomes 10 to power minus 7 ohm centimeter square minus 6 ohm centimeter square 10 to power minus 5 ohm centimeter square. So this transfer length is increasing. So here in this case, it's almost more than 4 micrometers. So it means this contact resistance, if it increases, this LT increases, and it is obvious, we have discussed in the earlier slide, physically as well as with the help of a mathematical equation. Here in this slide, you see uh, this transfer length as a function of contact resistivity is plotted here as the contact resistivity. You see here, this resistivity is increasing here, contact resistivity, this transfer length is increasing, that we have seen in the earlier slide also. But if we talk about uh, uh, the variation of transfer length as a function of sheet resistance of semiconductor for a fixed value of contact resistance, so the line will be like this. So this line means a constant value of contact resistivity. So if you see here, so for a constant value of contact resistivity, if the sheet resistance is changing, you see, when we are moving from this graph to this graph in upward direction, this sheet resistance is decreasing. This is 1000 ohm per square, this is 10 ohm per square. So when the sheet resistance of semiconductor is decreasing, this transfer length also, you can see it's increasing, right? So because as we are going up, this transfer LT is increasing. If the sheet resistance here that decreases, so current will prefer to travel more within the semiconductor before being collected by the contact, right? And read this line here. Typically, if you talk about a good contact, then its contact resistivity is should be something in this range, 10 to power minus 6 ohm centimeter square, and this transfer length is normally near about 1 micrometer. So these are important parameters which you should keep in mind when we talk about a good contact. Transfer length about 1 micrometer, and contact resistivity something in this range. Now, if we talk about the measurement of contact resistivity or contact resistance with the help of this transmission line model, so we have several structures. So one structure is like this. So you see here, again there are multiple contacts, right? And if we use this kind of structure, you see here, the current flows between this first and second contact, and voltage is also measured between first and second contact. And the contact which we are characterizing here, that is this contact. So this contact is the contact which is being characterized in this. We are assuming that the contact 1 is some ideal contact here. So, and when we are measuring this voltage between contact 1 and contact 2, it means the current which is entering here, that is collected by this semiconductor here, right? And the effective length which is being used here, that starts from this front end. So that's why this structure is known as contact front resistance structure, because the resistance which we are measuring, the contact resistance actually that we are measuring, that is at this front end. Now second arrangement is like this. So physically, if you look at the structure is almost same as this first one. The only difference is here the current is flowing between first and second contact, but voltage measurement is being between second and third contact. So this measurement, or you can say the contact which is being characterized, is again the second contact, right? But only difference is, since we are measuring voltage between second and third, so the resistance is being measured at this contact, right? Here the resistance was being measured at this front contact. So that way it is possible to measure this contact resistance at this contact, front contact, or at the back contact, right? So you have seen that the resistance, contact resistance, that depends at the end, right? Because most of the current will be like it's distributed in such a way that it is collected by the contact at its end itself. Whole area is not involved in the measurement. There is third structure also. So this is cross bridge Kelvin. So here the resistance is measured at this end. So, but this structure we are not going to discuss. That part will not be discussed. So our discussion is focused only in these two structures. So we will look at how to measure this contact front resistance and contact end resistance. This end and this end. So we are not going to discuss about this cross structure. So first, let's see how to find out contact resistance with the help of contact front resistance structure. So this is contact front resistance structure. You can see here the current is flowing between these contacts and the voltage is also measured between this first and second contact, right? So of course we are assuming that this Z is almost equal to W. So the correction factors we are ignoring. But remember, this is theoretical uh, arrangement. Practically there is difference between Z and W, and we have to add some correction factor. But for theoretical simplicity, here we are assuming that this Z is equal to W. So in that case, this contact resistivity is greater than zero point 0.2, and zero point 0.2 multiplied by sheet resistivity of semiconductor T is the thickness of this channel. Now, so only the equation is given here. The equation for contact front, contact front resistance, front end resistance, this end. So I'm marking here this end. This I'm calling front because current is entering from this side. Current is going like this. So for the current, this is front, right? And this is end part, right? So here we are talking about front contact front resistance. The equation of contact front resistance is given by this. So it's of course it's a ratio of voltage and current. Voltage which we are measuring with the help of voltmeter between these two contacts. I is the current which we are supplying from outside. So that will be given by this part. You see here sheet resistance of semiconductor is there and contact resistivity is specific contact resistivity is also there. L, which is the physical length of contact, and LT, which is the effective length of the contact, or you can say the transfer length of the contact that is there. So this part can be simplified because we know that LT, that is related to sheet resistance and contact resistivity, and that equation you can see from the earlier slides. So if you put the value of LT here, so this part will be simplified something like this. That you can simplify, that you can try yourself. If you have any difficulty in understanding how we got this, we can have a separate discussion about it. Now remember, this equation is not valid if Z is smaller than W. If Z is very smaller than W, then it is not valid. But I told you here we are considering that this Z is equal to W, right? Now this contact front resistance, that can be called as RC, contact resistance, simply contact resistance, if L is smaller than 0.5 L, right? Means the actual length of this contact, this is L from here to here, this end to this end. If this length of contact is less than half LT, right? It means transfer length is more, but physical length is small. What it indicates? It indicates that whole part of this contact is being used in the current collector. In that case, this term, this hyperbolic Cot function of L by LT, that will become equal to LT by L, right? So if you put this LT by L here, LT by L here, LT will cancel this LT. So in the denominator, what will be left behind? Z is already there, L will also come here. So the equation of RC will be this, right? So, but remember, it is possible only if this L is less than transfer length. And in that case, effective area, that will be L into Z. So you see here, in order to calculate this effective contact area, we are using this physical length itself, because we know LT is much bigger than L. It means whole L is being used in the current collector. So we can use this L. So the contact resistance or contact area is actually the effective contact area, right? They are same. So here you can see L by Z. In that case, it is possible that we can use this kind of simple equation that the contact resistance is uh, uh, it can be calculated with the help of actual, or you can say the physical area of the contact. But if this type of situation is there when L is very large as compared to LT, right? LT is large, LT is small and L is very large. It means definitely whole contact is not being used, right? So you should know LT in order to get the value of RC, in order to do the actual calculation. And if this kind of condition is there, the L is very large as compared to LT, so this function, hyperbolic cot function, that becomes equal to 1. So if you put this 1, what is left behind? This RCF is rho c divided by this, rho c divided by this. And I told you that we are saying that this RCF itself is your contact resistance. So the contact resistance is given by this formula, right? But remember, this LT into Z, that is effective area, that is smaller than the AC actual area, because a lot of portion of this physical contact is not being used in the current collection. So actual physical area is more, but the effective area is small, right? So depending on the situation, we can decide whether to use this equation to find out the contact resistance, or this particular equation for finding the contact resistance. But preferred thing is this. So while designing a contact structure, in the beginning itself, we should have some idea about all the parameters, so that we can estimate that how much is the actual LT, yeah, how much is the actual length of the contact which is needed for the transfer of current. So it should be avoided to fabricate like large contact, because that is of no use, especially when we are using a lateral contact or a horizontal current is being used in the structure. Then we have to plan in advance what should be the actual physical area of the contact. So that variation you can see here, that is actual length, physical length of the contact, and this RCZ parameter you can see here. So that varies up to this much part, and beyond that it remains stable. So front contact resistance, contact with product as a function of contact length, right? So beyond this, it's not responding. So the big length is not needed here. Now, transmission line model for contact and resistance. So I told you that the resistance occurs at this end, at this end. So if we are interested to find out contact resistance at this end, then we have to use this kind of arrangement. This is I, which is the current inserted between contact 1 and contact 2, and voltage is measured between contact 2 and contact 3. So then only this end will come into picture, and the resistance is being measured is the resistance at this end. So the equation of this resistance, contact and resistance, is given by this equation. So it is again simplified. LT is there in this equation now, and now it's possible to get some idea about the resistance here. And remember this equation of contact and resistance, and from the previous to previous slide, uh, contact front resistance. So if you find out the ratio of these two resistances, ratio will be given something like this. Now if contact is short, then the accuracy is determined by L, right? And if contact is long, then this contact and resistance is very small, and the accuracy depends on the instrument which we are using, right? So from today's discussion, now you understand that how we can find out contact resistance. We have seen many techniques for finding out contact resistance. There is two terminal to contact method, then there are multiple contact to terminal method, and so we have seen the advantages and disadvantages of various ways. We have seen transmission line model that describes that why uh, the actual transfer length is different from the physical length, and how we can use this transfer line structure to find out different end resistance and end resistance and contact resistance, and from these also we can find out the contact resistance. So if you have any doubt, any question, so you can discuss in the interactive sessions. In the next lecture, we will discuss one more technique for finding out contact resistance, and that is uh, transfer length method. So that we will discuss in the next lecture. So thank you very much.